Quiet down, please. Okay. Okay, so we're going to finish up with the inequalities that we looked at last time. So there were a few homework problems that are set. We're going to go through those. And then we're going to look at integral functions, okay, and the area function. Okay, this will then take us to the fundamental theorem of calculus, which is the major theorem for this semester and for next year as well. Okay, so let's have a look at those homework problems. Talking needs to stop. Yeah. So let's go through the homework from last time. Okay. So number one, we wanted to prove this inequality. So it was 2 less than or equal to the integral from -1 to 1, root 1 plus x squared dx is less than or equal to 2 root 2. Yeah. So we've got this double inequality there that we need to deal with. So some of those properties from last time we'll be using. Right? If a function's positive, then the area is positive. If f is less than g, then the area under f is less than the area under g. And then the one where f is bounded between little m and capital M. Right? Those inequalities, we need to be using those. Okay, so we've got this. What can we do? Yes. Yes, where the function is bounded. Okay. Now, there's a number of ways of doing that. We can do it that way. Maybe there's another way. Let's try it out. So we're going to see, is this function bounded? Bounded between little m and capital M. So little m, that's the lower bound. Capital M, that is the upper bound. Okay, so on this interval from -1 to 1, what would the minimum value be? Right? It's a continuous function on a closed interval. There's a minimum and a maximum. We know that. So what would the minimum value be? 1. I think someone said 1. Yeah. We put in x equals 0. We get 1. That's a minimum value. Okay, what about the maximum value? Square root of 2. If we substitute -1 or +1, we get root 2. That will be the maximum. Okay, and now we can just use property number 10. So m, the little m, times b minus a is less than or equal to the integral, less than or equal to capital M times b minus a. So b minus a, quick check, 1 minus -1, that will be 2. So we have m b minus a is 2, and capital M b minus a, that will be 2 root 2. So the integral lies between these two values. Therefore, 2 is less than or equal to our integral, which is less than or equal to 2 root 2. Yeah, very easy. We can use property 10 and then just find the little m and the capital M. Okay, good. Any questions for this homework problem? Yep, pretty straightforward. Okay, number 2, pretty similar. So we have pi over 12 is less than or equal to the integral from pi over 6 to pi over 3 sine x dx less than or equal to root 3 pi over 12. Again, we use radians. So the derivatives, we used radians. Integrals, we also use radians. Everything's radians. Okay, so again, we have this integral between two values. So we can use that property 10 again. Okay, because we need the little m and the capital M. So we've got sine of x. We're going to do a little sketch just to find that minimum and maximum. Okay, if you already see it, you don't need to sketch it, but it's fine to sketch it. So it's going to be something like this, right? And it goes up to 1 at pi over 2. But both of those bounds there, the lower bound and the upper bound, are less than pi over 2. So you don't need to draw it any further than that. Okay, pi over 6, that will be over here. And pi over 3, that will be over here. Right, so pi over 6, 30 degrees, pi over 3, 60 degrees. And then at the top there, that's our 90. We see that on this interval here, from 0 to pi over 2, it's increasing. Okay, so it's increasing from pi over 6, that will be the smaller value since it's increasing. And at pi over 3, it will be the larger value, again, because it's increasing. So from here to here, it's increasing. So the lower bound, that will give us the smaller value. So over here, this will be little m. And then the upper bound, that will give us the larger value, capital M. If this was decreasing, then it would be the other way around. Okay, the smaller x value would give you the larger function value, and the larger function value would give you the larger x value would give you the smaller function value. So just as a side note, if this was decreasing, so let's say this is a to b. Here we have f at a, f at b. You see it swap. So now a was the lower bound, that gives you the larger value, and b, that's the upper bound, but that will be the smaller value. Okay, because it's decreasing. So just keep that in mind. Okay, so if it's decreasing, it's the other way. So at pi over 6, we need to find little m. So that's just sine of pi over 6. What's that going to be? Special angle half, yeah. Okay, and then we need capital M. We said that was sine of the upper bound. Sine of 60. Root 3 over 2, good. Okay, and don't forget the b minus a. So b minus a, that will be upper bound minus the lower bound. So b minus a, that will be pi over 3 minus pi over 6. Okay, so that will be 2 pi over 6 minus pi over 6, so just pi over 6. Okay, and then we've got our answer, right? So b minus a times the little m, that will be our first value, less than or equal to our integral, less than or equal to b minus a times the capital M. Yeah, which is what we wanted to show. Any questions for this homework problem? Okay, I see a lot of people writing it down. You should have already had it written down because it's for homework. Number 3. We have the integral from 0 to pi over 2, x sine x. So we've got a product of two things. We want to show that this is bounded above by pi squared over 8. Okay. Now there's a few ways of doing this. So the first thing is, or the easiest way, sine x, we know that's bounded, right? Between -1 and 1. So that gives us a natural inequality to start with. So sine of x is between -1 and 1. And then we can build up to that function over there. Okay, so that's one way of doing it. Another way is it's a product of two things. And there's an inequality we can use for products. Over here, the Cauchy-Schwarz inequality. So we've got a product, f and g. If we can't integrate the product, we can split it up into one part and another part, and then do them separately. Yeah, that's another way of doing it. However, in our case, it's x sine x, right? So f will be x, and then we need to integrate x squared. So that's doable. We know how to do that. But then for g, that will be integrating sine squared. Again, it's doable, but it's a little bit more difficult. So we want to avoid that. Yeah, but again, it is possible. You can do it that way. But we're going to do it a little bit easier. Okay, so we know sine x is bounded. So we can start with that. Let's pick. Okay, so we start with sine x being bounded, and then we build up to what we want. So however complicated that function is, the integrand, we can always build it up from the starting point. Seems like this pen's giving up. Okay, very good. Okay, so sine x is less than or equal to 1. We don't need to include the negative part because we're looking for an upper bound. But even on this interval from 0 to pi over 2, sine x is positive anyway. So we didn't even need the lower bound. Now, what do we want? We want x sine x. So let's multiply both sides by x. Yeah, we end up with that. So what we have is some function, x sine x, is less than or equal to some other function, right? We know that if f is less than g, then the area under f is less than the area under g, right? From that property we had. Therefore, the integral from 0 to pi over 2, x sine x dx, is less than or equal to the integral from 0 to pi over 2 of x dx. Yeah. Now we just need to figure that out on the right there. But that's easy. We don't need to do the whole Riemann sum way that we looked at last time, because this x function just looks like this. And what we want is this area, right? Well, that's just a triangle, half base times height. Okay, so the base here is pi over 2. The height here is, what's the height? The function is x. It takes x, gives you x, pi over 2. Good. Okay, so this is going to be 1/2 the base times the height. Okay. That gives us pi squared over 8. Okay. Which is what we wanted to show here. So we have this complicated integral with x sine x, then we end up with a simpler integral with x, and we get our pi over 8, pi squared over 8. Okay. Any questions for this one? We said sine x is less than or equal to 1 because it is. It's our starting point. So we want to get rid of that x sine x, right? Because that's complicated. So we start off with sine x being less than 1, which we know is true. If we multiply both sides of the equation by x, the left-hand side is the function we have, right? And the right-hand side is a lot simpler to work with. Yeah. So instead of working with the left side, we work with the much simpler right-hand side. Yeah. We could have done the same thing. Maybe this for homework. Maybe we had something like this. X cos squared x. But it's the same game, right? We want to get rid of this complicated function. We know that cos squared is also less than 1. Right? It's cos squared, right? So we can have here cos squared is less than or equal to 1 from 0 to pi over 2. We multiply both sides by x. So we get x cos squared x, which is what we want. And the right-hand side is much simpler now. So we can do the integral on both sides using that property. And this other side just becomes this, which we did before. Yeah, so we replace the more complicated integral with something simpler. Okay. Any other questions? Oh, good. Okay, and then the last one, number 4. We had the integral from -1 to 1, root 1 plus x to the 4. Dx was less than or equal to 2 root 2. Yeah. Now here, if this was that double inequality with the smaller one less than the integral less than the larger one, we could use that property 10. Right? We can do that. So you can try that out. But since this is just a one-sided inequality, something less than or equal to something else, we can try something else. Okay, so let's start off with this left side and try to get to that right side. So we have the integral from -1 to 1, root 1 plus x to the 4. Okay, notice this is an even function. If you replace x with minus x, you get the same thing back, so it's even. So instead of going from -1 to 1, we can go from 0 to 1 and double the answer. Okay. Pretty easy. Now, on this interval 0 to 1, this integrand, the function root 1 plus x to the 4, will have a maximum value. A continuous function on a closed interval must have a maximum value. What will that be? Square root of 2. Yeah, you just substitute 1. You get root 2. So on this closed interval, it has a maximum value of root 2. So we can replace the integral with the maximum value. But it won't be equal anymore. It will be less than or equal to. Yeah, very easy. Any questions for the last homework problem? Yeah.
Yeah. And we do the log manual. We have again like 2 inequalities.
Yeah.
One.
Yeah, that's what we did here. We just looked at the right side, yeah. But there's no point in, looking for the little m and all of that. So we did exactly that, but we just found the capital M. So it's the same property, we're just doing half the work. Okay. Any other questions for the homework? Oh, good. Okay, so let's go on to today's lecture. Integral functions. Okay, so we'll look at this very generally, so what an integral function is. But then specifically for our case, we're going to be looking at the area function. Okay, but just keep in mind, it does get a lot more complicated than the simple case. Okay. I did mention this briefly before when we looked at elementary functions and non-elementary functions. But sometimes a function can't be written down using elementary functions. Okay, so what do we mean by elementary functions? Well, it's the ones that we've been using all along. So x squared, root x, e to the x, trig functions, logarithms, and so on. All of those standard functions that we've been using. So there are, in fact, functions that cannot be written down using those particular functions. Okay, very, very strange functions. We're going to look at a few examples, but later on you'll see a few more that you're going to be using, especially the electrical engineers. You do this quite a bit. Okay. These are called non-elementary functions. Okay. Again, electrical engineers, please make sure you know these words. Okay. Let's have a look at a few examples. Okay, so the first one is called the error function. Okay, funny name, but it's just a function. We write it ERF. Oh, Atlas pen. Okay, we write it ERF. Okay, of x is equal to 2 over root pi, the definite integral from 0 to x of e to the minus t squared dt. Okay. So that's called the error function. There's a lot of stuff you can do with this, signal processing and all that funny stuff you're going to do later on. But basically what this is, let's ignore the factors in front there, the 2 over root pi. What we have is a function e to the minus t squared, which we can draw. It's not too complicated. It looks something like this. Okay. It looks something like that. And what we want from this integral is the area under the curve, right? The integral is the area. So we want the area from 0 up to x. So from t equals 0 to some t equals x, which is a variable, it changes. We're looking at this area over here. Okay, it's scaled by the 2 over root pi, but don't worry about that. The main integral over there is just the area under the curve. Okay, from t equals 0, so that's our lower bound, to t equals x, that is the upper bound. Okay. And as we change x, right, from 0 to infinity, this error function just computes whatever that area is. So that's number 1. Then we have number 2, the logarithmic integral. This is going to be the integral from 0 to x, 1 over the natural log of t dt. Again, we can do a similar thing. We can draw the picture, and we can find the area from t equals 0 to t equals x. Whatever that value is, that's the value of this logarithmic integral. Okay, so again, it looks very complicated, but it's exactly what we've been doing before. Okay. Another example is the exponential integral ei of x. This is the integral from minus infinity to x. Okay, so a little bit strange. We're going from minus infinity to x. Again, don't worry, you'll see all of this later on. Minus infinity to x, e to the t over t dt. Okay, so again, you can draw this function. And then the area under the curve, that's the value of this integral function. Let's do one more example. The sine integral, okay, you definitely see this a whole lot, is equal to the integral from 0 to x, sine of t over t dt. In engineering, that's normally called the sinc function, SINC. So you got the sine function, cosine function. This is the sinc function. And again, in signal processing and circuits and all that electrical stuff, you're going to use that like every day. Okay, and so on. There's lots more. You can come up with lots of these integral functions. Okay, but what makes these ones important over here is that these are non-elementary. It means there is no other way of writing these functions down besides an integral. Yeah. So, for example, that bottom one, the sine t over t, there's no way to evaluate this using the functions that we know. Okay. That's the only way that we can write it down. So these non-elementary functions can only be written down as an integral. Now, the ones that we're going to be looking at are not these funny non-elementary types. What we're going to be looking at are functions where we can compute this. So we're going to have some integral of a function, and we can actually get some function from this. Yeah. So the area function. Okay, we're going to look at a very simple example at first, and then tomorrow during the tutorial, you'll be looking at other examples in a lot more detail. Okay, but for now, we'll keep it simple, and tomorrow you will do the rest for the TUT. Okay, so find the function a of x okay, that gives the area under the curve f of t equals t squared from t equals 0 to t equals x. Yeah, so this is some function a of x, and it will give us the area underneath the curve from 0 to x. Okay, very similar to what we drew over here. So we're going to have some function from 0 to x. We want that area. Okay, so let's set this up. So f of t is t squared. That's very easy to draw. So we have our very simple parabola. Now what we want is the area underneath this curve from that origin to some x value. Now this x value is just some value, could be positive, could be negative. For the picture, we're going to draw it as positive, but of course you could put any value there. Okay, so we're going to go from t equals 0 to t equals x. Again, I just chose a positive one here for the picture, but this x can be anything. And the area of this pink region, that is going to be our function a of x. Okay, so let's set up the integral, and then we need to solve it. So we know how to find the area under the curve. It's the integral from the starting point to the ending point. So this is going to be the integral from 0 to x of our function, which is t squared dt. Okay. And this is an integral function. It's a function defined as an integral. Now, this is not those non-elementary types. We're going to figure out what this actually looks like. Okay, so let's evaluate this integral and see what function we get. Okay. Now there's a short way and a long way. For some practice, we're going to do it the long way with the limits of a Riemann sum. And then next week, we're going to look at the much shorter way. Okay, so long way using limits of Riemann sums. Okay. Please do not delete that from your brain for the next class test. Okay, so it was on the previous class test. It will be on the next class test as well. So let's set this up. Notice here we are integrating with respect to t. Okay, so we're not going to have delta x and f of x and all of that. It will be in terms of t. Okay, so please do not mix that up. Okay, so we're going to have a delta t. That's going to be the upper bound minus the lower bound over n. So the upper bound is x, the lower bound is 0. So it will be x over n. Again, please do not let this confuse you. The x integrals we looked at last time, that was delta x, xi, f of xi. This is now in terms of t. Okay, so please do not mix up your variables. So we're going to have ti, that will be a plus I delta t. So that will be xi over n. And finally, f of ti, that was just t squared. So that will be x squared r squared over n squared. Okay, so we've done the setup. Let's substitute into the formula, and then we need to evaluate the sum and then the limit. So we have the limit, n goes to infinity. The sum, r goes from 1 to n. F of ti, not xr, delta t. Okay, so it's the same shape formula. Again, we just have a different variable there. So this will be the limit, n goes to infinity. The sum, I goes from 1 to n. F, we have that over there. So x squared, r squared over n squared. And then the delta t, we have that up there, x over n. Okay, so x squared and x, that will become x cubed. That has nothing to do with I or n, so we can take it out to the front. Then we have the limits, n goes to infinity. The sum, r goes from 1 to n. Then we have r squared over n cubed. Okay, quick check if we left anything out. The degree of the top is 2. The degree of the bottom is 3. So we've done everything correct so far. Now, n cubed, that has nothing to do with I. We can take it out of the sum. We can't take it out of the limit though, but we can take it out of the sum. And then we have the sum, I goes from 1 to n of I. Great. We know what that is. Okay, so this over here. n plus 1, 2n plus 1 over, what's the bottom? 6. Good. So we can substitute. So this will be x cubed. The limit stays. Then this will be n plus 1, 2n plus 1, all over 6. Okay. And then we have the n cubed over there. Now we have n at the top, n cubed at the bottom. We can do a bit of cancelling. So cancel, cancel, and we can write n squared at the bottom. Okay. The top part there, the 2 brackets, we can expand that out. And then the 1 over 6 we can take out, so we have x cubed over 6. Limit n goes to infinity. We're going to have 2n squared plus 3n plus 1. all over n squared left. Okay, so we expand it out. Now the last bit separates it so that we have something over n, and then take the limit. So limit n goes to infinity. 2n squared over n squared, that will just be a 2. 3n over n squared, that will be 3 over n. And 1 over n squared, 1 over n squared. Okay, if we did everything correct, anything with n, that will immediately go to 0. Okay, so everything's fine. There's no n's at the top. The only n's are at the bottom. So all of that goes to 0. Okay, now we just have the limit of 2. That's just 2. 2 over 6, it will be 1/3. So we have 1/3 x cubed. Okay, so this complicated looking thing on the right here, this integral function, we can evaluate that, and that gives us 1/3 x cubed. Therefore, a of x is equal to 1/3 x cubed. Very simple. So for any value of x, substitute it in, that will give you the area under the curve from 0 to x. So this will give the area under t squared from 0 to x. All right. Any questions about this example? Yep. Pretty simple. So you're going to have 2 homework problems, and then the rest of it you're going to see tomorrow during the tutorial. Okay, please make sure you do these problems, otherwise you're going to be a bit stuck tomorrow. So number 1, f of x equals the integral from 0 to x, e to the t dt. And number 2, g of x, that's the integral from 0 to x, sine of t dt. So f, that is the area function for the exponential, and g, that is the area function for sine. Yeah, please do these for tomorrow. Any questions about the area function? All good. Okay. Now, last thing for today. We started with this function t squared over here. Yeah, that was the function we're looking at. This area function ended up being 1/3 x cubed. What do you notice about those two? It's the antiderivative, yes. And we'll see that works not only for this example, but for any function. So if you find the area function, as we defined it here, for some function little f, we end up getting capital F, the antiderivative. So given little f of t, the antiderivative. Yeah, remember, we had all those, that whole table with the antiderivatives. So to find those, we started with the derivative and we worked backwards, right? Now this way is working forwards. So we have a function and we can explicitly write down the antiderivative. So the antiderivative is given by capital F of x is the integral from little a, doesn't have to be 0, little a to x, f of t dt. Okay. So given any function little f, we can find the antiderivative this way. Right. Any questions about this? Okay. and then just a little note, this little a over here. Please do not think that that bottom part is always 0. So for these examples, we went from 0. That's just to make the homework a little bit easier for you. However, this can be any real number. Okay, and changing that little a there is equivalent to changing the plus c that we had before. Okay, we'll see all of that later. Changing a is the same as changing plus c. Okay, so we'll see all of that on Thursday when we do the fundamental theorem of calculus. So on top of the homework problems here, please read through that for Thursday. Okay, so in the textbook, you have these problems here. You just turn over and you'll see the fundamental theorem of calculus part 1. And part 2 we'll look at later, but part 1, please read for Thursday. Okay, the fundamental theorem of calculus, part 1. Okay, part 2 we will cover in the following weeks. Right, any questions? All good. Okay.